Good morning, good afternoon, everyone. We'll give it just a minute or two while everyone works to pop in. Giving it just a few more moments. There's still some people hopping in the room. All right, I'm going to go ahead and get us started. Hello, welcome everyone to Oliver and ClorDiSys webinar, Alternative Sterilization for Healthcare Packaging, a Chlorine Dioxide Deep Dive. I'm Haley Schraben, Director of Product Strategy for Oliver Healthcare Packaging, and I'll be your moderator today. We've got just a few brief announcements before we begin. The first is that this webinar is designed to be interactive. So in the right bottom of your screen, you'll have the opportunity to click chat or Q&A. If you're experiencing any technical problems, please use the chat function and someone on our end will do our best to help to assist you. And then you can use the Q&A function to ask questions that relate to the content of the presentation. You can also check a box to make sure your question is asked anonymously if you would prefer to do that. And now on to the presentation. Today's agenda will begin with an overview of chlorine dioxide sterilization, including what the gas is, the typical sterilization process cycle and validation, and its compatibility with medical devices. We'll then discuss chlorine dioxide sterilization compatibility with packaging materials specifically, including results from a recent aging study on several common sterile barrier system materials. And finally, we'll wrap things up with key takeaways. But before we dive into chlorine dioxide specifically, we thought it would be a good idea to ground the audience in what is happening in industry. So today, almost all single-use sterile devices are sterilized via ethylene oxide or gamma radiation. In the US alone, about 20 billion devices are sterilized by ethylene oxide annually. But due to regulatory and supply chain pressures, there's incentive for organizations to explore alternatives and diversify those options. To be clear, ethylene oxide and gamma aren't going anywhere. They've got broad compatibility, excellent penetration, and they're positioned to handle high volumes. So what this actually looks like today is more of an interplay between established and then emerging technologies. Today, we'll be exploring chlorine dioxide sterilization in more detail. Our goal is to give packaging partners the knowledge and language that they need to collaborate with sterilization owners in their respective organizations, to provide guidance for you to effectively collaborate with cross-functional decision makers by knowing which questions you should ask and then maybe even which assumptions you should challenge when considering chlorine dioxide as a viable sterilization solution for given applications. So before we dive in, let's kick things off with a poll question to engage the audience. What alternative sterilization modalities is your organization exploring? And you can select all that apply, so please choose more than one if applicable. All right. Oh, good. A good variety. Lots in E-beam and X-ray, also a very good amount in vapor hydrogen peroxide and chlorine dioxide, as well as some others. Excellent. Okay, great. All right, discussing today's topic are two industry experts. First, we've got Jeremy Elwell, Technical Services Manager at Oliver. Jeremy has a degree in packaging from Michigan State University and has over 20 years of healthcare packaging experience across design and development roles. Next, we have Emily Lorcheim, VP of Sterilization Technologies for ClorDiSys Solutions. Emily is a chlorine dioxide subject matter expert working with medical device manufacturers to generate sterilization strategies that fit their unique applications. She's also involved in several industry working groups conducting studies to increase availability of chlorine dioxide sterilization data and leads the Kilmer Chlorine Dioxide Modality Group working to accelerate acceptance of alternative sterilization modalities by our industry. So with that, one more poll. Let's kick it off with one more poll before I hand it over to Emily. Is your organization evaluating chlorine dioxide as a sterilization modality? Yes, no, or not sure? This will give Emily some good information as she jumps in. Okay, about 20% said yes and some not sure. Okay, good. So lots of room for you to educate the audience here, Emily. I will hand this over to you.
Thank you, Haley. So now we're going to talk about chlorine dioxide and the overall background on the technology. So chlorine dioxide has a yellow-green color to it. So if we were to put it in a isolator, so a sealed clear box, you would see that color. And that color is a benefit because we're able to monitor it via UV-vis spectrophotometer. This gives us an accurate concentration and we can calculate a precise dosage off of that. So it's very highly controlled and highly monitored, more so even than ethylene oxide. It's also water soluble, so say there was any water in a chamber, the chlorine dioxide would penetrate and form a chlorine dioxide solution. It won't dissociate like other sterilants would. Its boiling point is minus 40 degrees Celsius. Now, the importance of that is that it's a true gas. A true gas allows it to penetrate tight areas, get through packaging. If it was something like a vapor, it's going to condensate on a surface and not get into those tiny to reach areas. So things like lumens, again, packaging, all able to be sterilized with chlorine dioxide. Chlorine dioxide is also non-carcinogenic, non-flammable, non-explosive at use concentrations. So those are key things when looking at an ethylene oxide alternative. Ethylene oxide is facing a lot of environmental issues right now, mostly the carcinogenic aspect of it, both with emissions and its residuals. And because chlorine dioxide is not explosive, we're able to sterilize things with embedded batteries, as well as other sensitive electronics. A difference is that it is an oxidizer. Now, most of the alternative sterilization methods are oxidizers. However, chlorine dioxide is the most compatible with materials of the oxidizers out there. Now, with ClorDiSys chlorine dioxide gas, the way we generate it, it is considered an EPA-registered sterilant. So when looking for alternative sterilization modalities, it's important that what you're looking at is truly registered with the EPA. Now, a sterilant meaning it achieves a 99.9999% kill of any organisms present. Our site in New Jersey is also registered with the FDA as a contract sterilization facility. We have ISO 1345 certification. There's chlorine dioxide gas sterilized medical devices on the market, both in the United States and CE marked devices in Europe. And there's pharmaceutical products sterilized both in the US with FDA, Health Canada, and EMA in Europe. So some differences. Again, there's a lot of different methods that you can use for sterilization. However, most people here are probably looking to turn away from ethylene oxide or at least considering it. So some differences between the two or comparisons. Chlorine dioxide, again, is non-carcinogenic. It's also non-explosive. They're both sterilants, though. So both very good. There's no issues in terms of that when comparing against each other. Now, some differences here. For the majority of this cycle, or majority of products and situations, I should say, the entire process occurs within the chamber. So this includes everything from preconditioning through aeration. Preconditioning generally is 60 minutes at ambient temperature, whereas ethylene oxide, this can last for many hours to even days and often is a heated environment. So if you have a temperature sensitive device, it's not necessarily compatible. Now, you do want to humidify your product in your sterilization load. This is to open up spore walls to allow a sterilant to penetrate. Now, this is roughly between 65 and 75% relative humidity. But again, chlorine dioxide requires a much shorter time. Also, you can have a ambient or vacuum pressure sterilization process with chlorine dioxide. This gives a little bit more flexibility, especially if you have things like a plunger and a pre-filled syringe, or if you have packaging considerations where excessive vacuum would be harsh on it. Now, the necessary cycle parameters for chlorine dioxide are humidification, gas concentration, and dosage. It's a little bit different with ethylene oxide, mainly being the heat component to it. So ethylene oxide needs to raise the temperature of the process in order to get better efficacy. Also, time is more of the controlled measure rather than dosage. We can have a varying time exposure, but as long as we maintain that dosage, we see consistent kill. The biggest difference, though, is the aeration phase of it. For a chlorine dioxide gas cycle, it's generally 30 minutes, and varying by only a minute or two off of that 30 minutes. So very, very quick. It's conducted through only a series of vacuum exchanges within the chamber, whereas with an ethylene oxide cycle, this can be multiple days and often heated. Now, with residuals as well, chlorine dioxide gas has no harmful residuals, whereas ethylene oxide has carcinogenic residuals. So both are, again, good sterilants. Chlorine dioxide is a much quicker process, and both, too, considering packaging, can handle very similar packaging types. Now we're going to just briefly talk into validation and cycle development. Again, this is very product specific, but we'll give a brief overview. So it's basically the same process as you would follow with ethylene oxide. So we're going to follow instead ISO 14937 versus ISO 11135. However, it's almost identical with only a few key differences being the lab testing, mainly in the terms of residuals, whereas our residual test method follows ion chromatography testing, looking for the potential byproducts of chlorite, chlorate, and chloride. And also, in terms of process characterization, it's again different because it's a different sterilant. However, there is a new AMI TIR, which is TIR 124-1, and this is how chlorine dioxide relates and is applied to ISO 14937. So it makes it a very simple process, especially when you're familiar with ISO 11135. So this is just a little basic on the chlorine dioxide gas cycle. So again, almost identical to how ethylene oxide looks. So we're going to have preconditioning. We're going to first do a leak test and then raise the humidity level, generally 65 to 75% relative humidity. We're going to let that humidity sit in the chamber with the product for a specified period of time, typically 60 to 90 minutes. We're going to introduce chlorine dioxide gas into the chamber, leave it sit there for a specified time period until we reach our dosage. And then we're going to remove the gas through aerations. And this again is done through a series of vacuum exchanges sent through a carbon scrubber. And there's no chlorine dioxide gas emitted. However, you can emit chlorine dioxide into the environment, and it's completely safe to do so. So again, most of the time, the entire process occurs within the chamber, can be done at ambient or vacuum pressure. And again, cycles are typically 4 to 8 hours.
All right, so we'll engage the audience one more time here with a poll question. Which sterilization parameters are most critical to packaging material and design decisions? And again, you can select more than one answer here. And it's not a right or wrong, but we're curious what everybody's thoughts are on what is the most critical to packaging. Good, heavy mix across all four. So both Jeremy and Emily, anything you'd like to comment on there?
No, I think that's very interesting, the different opinions on that. And I think all can be very important in different aspects. And I think Jeremy's results that he'll present will help give further information.
Agreed. Yeah, there's a lot of the combinations of these different attributes as well that we'll go into and how they can affect packaging, but very good insight.
Right. Continue on, Emily.
So just getting more in depth on the critical parameters that were just in the poll. So with concentration, again, this is going to be what's sent into the chamber. We can fluctuate that. Typically, it can be zero point 0.5 milligrams per liter all the way to 30 milligrams per liter. The main difference is that with a lower concentration, you're going to have a longer cycle time to get to your validated dosage, whereas a higher concentration is going to be a shorter time. There may also be an impact on material compatibility, but that can be tested. And again, that may be based off of your material choices that are used. Dosage is the product of concentration and time. So just as I mentioned, it's going to be concentration and time. That gives you your dosage, and dosage is what you would validate because you can have a consistent one as long as you fluctuate those other parameters. That dosage is what's going to indicate lethality. Relative humidity, as I mentioned, helps aid in spores opening up and allowing the sterilant to penetrate. And the key thing, though, is that relative humidity in the conditioning time may need to increase with added packaging. So when you want to send your product to be validated, we'll evaluate your packaging selection in determining what kind of conditioning time is necessary, as well as what relative humidity is proper. For pressure, we can do from ambient, and typically we'll pull down in our deepest vacuum to 5 kPa, just to explain why you may need to fluctuate your pressure. So if you have a device, a simple device, no extensive lumens or tiny, crevices in your device, you can have just ambient pressure. So almost think about, say, a Band-Aid in a Tyvek pouch. That could handle just ambient pressure. Now, if you do have secondary packaging or tertiary packaging or a lot of complex design in your device, that's when you would introduce vacuum. So most medical devices and pharmaceutical products do require pressure. Now, you can also adjust that pressure level to be more suitable for your device. So going into equipment and some real life applications for it, we're going to talk about our Staradox 100. So this is just our one pallet chamber that can be utilized for chlorine dioxide gas. There's also multi-pallet chambers or even R&D size chambers, but this is just to give a visual for everybody. And on this page, again, it's just a blank screen, but the key thing here is that there are a lot of variables you can adjust to be more compatible for your product. Now, for instance, with packaging, say you had a blister with a Tyvek lid, and with a deep vacuum, you see that Tyvek lid moving around. You can lessen that vacuum to make sure that you don't have any popping of seals, etc. You can also adjust things like humidity levels, conditioning time, so on and so forth. So a lot of flexibility to provide the most benefit to your product. Now, I did mention that with chlorine dioxide gas, it will break down into chlorites, chlorates, and then into chloride. Most of the time, you don't even see these ions detected after sterilization, and you'll even see levels, especially of chloride, before sterilization. So what we do is we take a control sample and a sterilized sample and test them through ion chromatography testing. But again, in most instances, you don't even see an increased occurrence of ions found. So you would do this mostly on your device. However, a lot of people do it on their packaging as well. And this is important too, because with ethylene oxide, you do see those fugitive emissions and a lot of concern with that residual ethylene oxide, especially contained on cardboard boxes used for shipping. So we're going to talk about material compatibility again briefly. We can provide extra studies if anybody wants more information, but we'll give a brief overview here. So chlorine dioxide also has been added to AMI TIR 17, which is the compatibility of materials subject to sterilization. But it's just to give an overview, it's compatible with most materials. So stainless steel, anodized aluminum, plastics, polymers of any type. Now, there are some things where different additives may cause some yellowing, potentially some polycarbonates with bromine additives, so on and so forth. And with any sterilization modality, you will want to test your device with the sterilant because anything can be, not cookie cutter with that. Now, the big thing is that it is compatible with cellulose materials and electronics like embedded batteries. That's a different than most other alternative sterilization modalities, and ethylene oxide isn't compatible with batteries. Like I mentioned, chlorine dioxide is an oxidizer. However, chlorine dioxide is the most gentle of those. Going into different packaging. So things you can think of in terms of compatibility and what types that are compatible with the process. So for primary packaging, you want something that gas will be able to penetrate. This meaning not a sealed foil pouch. You can have foil as long as there's a Tyvek header, but typically you'll see Tyvek in film-based pouches or solely Tyvek. Now, in terms of secondary packaging, you can have single-walled shelf boxes, corrugate, single-walled fiberboard, and you can also have instructions for use. Same thing with tertiary packaging. Chlorine dioxide can handle corrugate boxes. Coated corrugate may allow for less absorption of humidity or the sterilant, or even other types of tertiary packaging. Now, this again is different than the alternative sterilization modalities because a lot of those cannot handle cellulose material. And then just to give another little overview before we send it off to Jeremy, chlorine dioxide is an ambient temperature process. We can have a gas concentration that can fluctuate depending on your needs for your process. The relative humidity is typical for other gas sterilants, 65 to 75% relative humidity, and a cycle time is relatively short, meaning 4 to 8 hours on average. We can have vacuum levels that can fluctuate depending on your needs, and we have a very rapid aeration process. So as I mentioned, we're going to go off to Jeremy to dive deeper into compatibility of packaging with chlorine dioxide.
Thanks, Emily. And when we start talking about primary packaging, we're talking mostly about flexible sterile barrier packaging materials here. And when that comes to mind when we talk compatibility, the first place I go in my head is what materials can we use? There are going to be other considerations, but starting with materials, and Emily, you've talked quite a bit about this already, but we have general good results with all of our studies with Tyvek, both coated and uncoated, cellulose products, including medical grade papers and corrugate, polyester and nylon-based pouching films. So that's where we'll start with this. And then when we look at risk with tray configurations, tray and lid, or pouch configurations, here's a couple we like to highlight. With any type of gas sterilization that uses vacuum, and chlorine dioxide does go at ambient, but also has some situations with vacuum, there is a risk of seal creep. And then also film delamination with some extrusion laminations, both of which we'll go into a little bit more detail in the next slide. So starting with film delamination, this is a phenomenon when layers of film separate after exposure to extreme conditions. We have written here EO cycles, but also any type of gas sterilization combined typically with accelerated aging and maybe other stack testing afterwards. And typically it's cosmetic. And if you do testing on the sterile barrier, you're not really always going to see a breach of sterile barrier, really just an eyesore. The film's separated from itself, and it looks like it's probably weaker, but it could pass further testing. So we do call it cosmetic to begin with until that further testing is performed. So some mitigation options, we talked about these being extrusion laminations, which I'll have a photo of later with a study that we have. A mitigation option is to use an adhesive laminated film, and that's much stronger. It could withstand these extreme environments, but also gas sterilization like chlorine dioxide. And also looking in further into extrusion laminations, there are primers that are compatible with extrusion, so you can also use those or consider those for your testing and appropriate levels of stack testing as well. There's a lot of guidance out there. There's a lot of standards we have to follow in the packaging world. Really understanding what testing is necessary and trying to avoid unnecessary stacking of those tests. And then another risk is seal creep. So seal creep can be defined as partial or complete separation of a seal after exposure to a stressful environment. So again, within sterilization, many types of sterilization, you have a combination of sometimes heat and vacuum. And when you combine that with low porosity or blocking porosity, you could have a difficult time getting the air in and out, and it could put stress on your seals. So some mitigation options are ensuring porosity is adequate. So using Tyvek, even medical papers, just ensuring that that is adequate in the design, but also the packaging design, the system design, and protective packaging, making sure you're not blocking that porosity is essential as well. And also proper material and adhesive coating selection comes into play. And we'll talk a little bit more about that here on the next slide as well. So what we're showing here is a comparison of creep resistance of different material combinations. So on the left is what we're calling R&D material with poor seal creep resistance, and on the right is good seal creep resistance in a commercialized product. So the note at the bottom, same starting seal strength, so somewhere around 1.5 pounds per inch in an unsupported F88 test. They start with the same seal strength, but if you put them in this chamber, and this is a 55 degrees Celsius chamber, so over time, the picture on the left with that R&D material with poor seal creep resistance, that rod is going through the seal after about 2 seconds. And on the right, we show about 10 seconds, but this could maintain up to, or I'm sorry, 10 minutes. We could maintain this time-lapse camera. We could maintain further than that with a well-designed packaging system. So between these two, we're just showing that material selection is very important, and that can help you mitigate risks within a gas sterilization cycle like chlorine dioxide that uses vacuum. So at Oliver and partnering with ClorDiSys, we have performed a packaging compatibility study, and we'll go into some of those results here on the next slides. First one is just a summary showing the cycle parameters that we used at ClorDiSys, and then some of the material combinations and pouch are the type and format, meaning some were pouches, some were lid sealed to PETG strips. We also had high density polyethylene cards in this study. But some of the highlights in here, we talked a little bit earlier about adhesive lamination, extrusion lamination. So we want to point out that we did a combination of those, and moving forward, what we did see with some of these results. And first, this is a uncoated Tyvek to peelable nylon pouch. And that structure, that diagram in the upper left-hand corner is a detailed breakdown of the layers of the film. The outside being biaxially oriented nylon. This is an adhesive lamination showed by the adhesive in the structure. And then on the inside, in the interaction with the Tyvek, is a peelable sealant. And these results show seal strength, puncture resistance of the film, tensile strength of the film, starting with non-sterile, post-chlorine dioxide sterilization, and then over accelerated aging time points of 1, 3, and 5 year. And this box and whisker plot of all of these show, not much effect over time or by the chlorine dioxide sterilization. So with this combination, we're very comfortable with recommending to this application. And just repeating this on the further slides, this is basically the same approach. This is just a peelable polyester sealed to uncoated Tyvek. So everything's the same, but in the diagram, you can see that the nylon from before in the previous slide is replaced by polyester in this film structure. So nylon, polyester, both showing the compatibility through seal strength, puncture resistance, and tensile strength of the film. And then we look at coated Tyvek with tray material, in this case, 11 mil PET G. So we're doing seal coupons. We're not taking fully formed trays in this study, but small seal coupons just to show seal strength over time and any kind of visual anomalies that we may see. But in this case, both a seal science or water-based type coating and a exhale or hot melt type coating, they both showed compatibility and no adverse effects over time. The one area that we talked about before with film delamination did come up in this study, and it really was expected. In this situation, this was when the chlorine dioxide chamber had the vacuum added to it. And so it really exemplified this and amplified this issue that we sometimes see. So this was expected, but with some extrusion laminations, this film delamination can occur. The picture below shows the wrinkling or those lines throughout. That's those two layers of film separating from each other due to the failure of the primer in between. And in that structure, the primer is not shown, but the nylon and the LDPE layers are separating from each other after exposure to chlorine dioxide. So this doesn't happen in every situation, just with certain materials that are extrusion lamination and in that vacuum type environment that we've seen so far. And if you'd like any more information, these studies are available upon request. So there's a lot more material combinations available, a lot more data, graphs, and recommendations throughout those reports that are yours for viewing upon request.
Now we're going to talk about cytotoxicity testing. So not only do you need to evaluate the biocompatibility of the device itself, but following ASTM F2475-20, you also need to evaluate the cytotoxicity of the areas of your packaging where the device touches. So we did a broad sampling here of different packaging types and seeing if they were cytotoxic. So we have blisters with Tyvek trays, we have or Tyvek lidding, I should say. We have Tyvek pouches. We have FFS packaging. We have blisters again with Tyvek lidding. All of these had non-cytotoxic results. So just showing overall biocompatibility results on chlorine dioxide gas sterilization are very suitable. Now we're going to go over a little brief summaries. There are similarities to ethylene oxide. Both are true gaseous sterilants. They're compatible with cellulose materials. Again, not all sterilization modalities are. Multi-pallet chambers are offered, so the scale-up process is very easy with chlorine dioxide. We can do complex devices. Also, again, large volumes, and we have broad compatibility with sterile barrier packaging materials. Differences, again, non-carcinogenic, non-explosive, very quick cycle times, zero emissions, non-detectable safe residuals. You can have sterilizers brought in-house, or we can do contract sterilization at our ClorDiSys facilities, and we can even convert ethylene oxide chambers to chlorine dioxide chambers. Now we follow ISO 14937, which is different from ethylene oxide standard. However, again, very similar process.
All right, so some final takeaways, and then we'll move into Q&A. Chlorine dioxide is a proven safe and effective method for sterilization of medical devices today with broad device compatibility, and there's advantages in the form of fast cycle times and flexibility in where a device gets sterilized in the manufacturing process. So options for in-house as well as contract sterilization. It's also compatible with a broad range of sterile barrier packaging materials, as we just reviewed. With that said, as you saw also from a parameter perspective, it's important that you understand those critical cycle parameters that can impact packaging so that you're ensuring you have an effective design to protect the device, maintain sterile barrier while also getting proper sterilization. And finally, industry working groups are collaborating to collect data that will support standard development, which Emily alluded to a little bit throughout the presentation today. And this will ultimately make it easier for industry to adopt and validate alternative sterilization modalities such as chlorine dioxide and some of the others that we saw at the top of the presentation. So thank you, Jeremy and Emily, for a great presentation. We're now going to move on to the Q&A portion of our presentation. As a reminder, you can use that Q&A function for this, not the chat box, please. And I'll kick things off here. Emily, this is a pretty simple one, but I think we could just maybe go into a little bit more detail for the audience. How big are chlorine dioxide chambers? I know you sort of hit on it, can go from an R&D size up to a few pallets, but anything else that you'd want to sort of shed some light on there?
Yes, so like I said, R&D chambers that might be good for just small scale. Like our facility will do initial feasibility testing on that. If you did have the need to incorporate that within your facility for small volumes, that is also suitable. Then we have 1 pallet, 4 pallet, 6 pallet, and even we're building a 20 pallet chamber right now. So very easy to scale up with the chlorine dioxide gas process. And that way we can meet the demand that current ethylene oxide customers need for a sterilization modality.
Right. And then Emily, this one's to you too, I think. So with so many variables, and I think they're meaning cycle parameters that you can customize, what does it typically look like when you start with a new device and figuring out what those parameters might need to be? How long does that take? What does that process look like?
So the first step really is looking at the device itself and determining what the worst case location in the device is to sterilize. So for instance, say you had a 1 meter long catheter, we would put a biological indicator, which is a spore strip, a million spores on it, which if we kill that, it's indicative of sterilization level kill. We would put that at the end of that 1 meter catheter. So the gas has to travel all the way through in order to kill it. So we would place the BI there. If we didn't know what that was based off of the customer, we would do the evaluation on that. And then we would place it in any packaging that was going to be in the, I'll say, final form for its validated state and do testing at that, determine what the level would be in order, in the validation terms, the half cycle where it would get kill on all biological indicators and then move on from the process there. But it's almost like a stepwise process. However, it's just starting small, making sure we can get kill and it still has good material compatibility, and then working our way up from there.
Okay, great. And then this one might be sort of for both of you. So we talked a lot about how chlorine dioxide is an alternative for ethylene oxide. Is it fair to say that it's a better alternative for ethylene oxide than for maybe a radiation type sterilization? So if someone were to be looking to go from maybe gamma to something else, is there any reason that they shouldn't consider chlorine dioxide for that? So I know we talked a lot about, comparing chemical gas to chemical gas, but what about comparing chlorine dioxide specifically to some of the radiation modalities?
So I heard at one time from an industry expert with radiation that no matter what, you're going to have material changes when you put a product into radiation. So you may have better material compatibility if you do opt for chlorine dioxide. Again, it may depend. And also, I've also been told by certain manufacturers that they would be able to switch to a less expensive material if they turn away from radiation and go towards chlorine dioxide. So there are instances where you may opt for switching away from radiation and going towards a gas method.
And for packaging compatibility, going from a gas to a gas, you're probably going to have, less work to do. It's going to be more transferable. If you look at radiation of any kind, going to or from that to a gas, probably a little bit more, just general material compatibility questions. And that goes down to packaging as well. But there are situations where it could be pretty straightforward as well, too.
Okay, great. All right. Another one, and this is around device materials, Emily. So you may or may not have an answer to this one, but I thought I would see if you've had any experience. I know we talked sort of high level device material compatibility with chlorine dioxide gas. There was one question around intraocular lenses, which use hydrophobic special polymers. Have you done any testing yet with any specialized polymers like that where you would be able to allude to compatibility? And it's okay if it's no, but.
But no, that was actually the very first application of chlorine dioxide gas. So our technology was developed within Johnson and Johnson, and they had intended for it to be commercialized, the gas process, commercialized with an intraocular contact lens. So they ended up selling off that company, but found the chlorine dioxide gas sterilization process so valuable that they pulled that away from the technology and kept it internal. So in short, it is compatible with that, and it's very good because there are little to no residuals for that.
Great. Okay, then I can take this next one, and I'm going to sort of segue it to you on a secondary question, Jeremy. But the question was, does Oliver specify on our website compatibility of certain materials or products with chlorine dioxide, or do we put anything on our spec sheets? We're pretty high level on our website today on compatibility with our products and modalities in general. And while many of our data sheets today do talk about compatibility with ethylene oxide or gamma radiation, we haven't updated them on any other modalities yet. Part of the reason is kind of what Jeremy alluded to. So much of this is dependent on your final product configuration and the two or sometimes even three sterile barrier materials that you're combining at once. So what I would point you to is those reports that Jeremy talked about towards the end of this presentation to start, where we do have all of the data, sterilization and aging on chlorine dioxide with specific materials and combinations of our pouch and even coated Tyvek with PETG options to get you started if you want all of that data. But Jeremy, the sort of secondary question on this, sample sizes that we used in those studies, anything that you want to speak to on that? I know we choose our sample sizes and something that we think is of value to industry, knowing that they've still got some of their sterilization and aging testing to do with their specific devices and sterile barrier systems.
Yeah, and this is a feasibility study, so we're not claiming any type of validation on this. So there's not really a protocol report sort of approach, but we have standard approaches, usually sample size around 30 for seal strength, and we'll follow standards and their recommendations for some of the attribute testings of the testing of the materials themselves. So that's all available in the report. It's all going to be laid out section by section about what we decided to use. But really, it's just a starting point. We plan to continuously collect data with feedback from industry to really understand what can be beneficial for each organization and try to implement that, including sample sizes and other attributes of a test and what types of tests in the future.
Thanks. And then Emily, I know we hit on this, but I think it'd be good to just reiterate for the audience since the question popped up. Actual chamber times for chlorine dioxide versus ethylene oxide.
So they can be a tenth of the time to even greater than that. So again, a typical chlorine dioxide gas cycle from preconditioning through aeration, meaning you can handle the product to right after, is generally 4 to 8 hours, sometimes shorter, sometimes longer. Longer meaning more packaging potentially or more complex device. But an ethylene oxide cycle can be days to even a couple of weeks from start to finish in the process.
We probably have time for just one more here. Emily, I'm going to shout this one out, but you might need to sort of parse through it a little bit. It's how significant is the endotoxin reduction with chlorine dioxide?
So that's actually something that we've seen in the past. We've done studies with a device manufacturer by spiking E. coli endotoxin on 304 stainless steel and 316 stainless steel, and we saw a reduction in endotoxin. So on the 316, we saw a complete elimination. On the 304, a slightly reduced but not completely reduced endotoxin. So we're going to do, and that might have been an absorption or other measures. But again, it was very simple testing. So we're going to start a new endotoxin study to evaluate if we can eliminate or reduce endotoxins, I should say. And that should be starting within the next month or so.
Okay, great. Well, that is all the time that we have for today. So thank you again so much, Jeremy and Emily, for your time. And thank you to everyone in the audience for participating today. If we didn't get to your question, or if you think of some other things that you want to ask or talk through later, please don't hesitate to reach out to Jeremy or Emily on LinkedIn. You can also feel free to shout out to myself or Jeremy if you've got a request for any results from the studies that we've done so far, and be on the lookout for other studies that Emily and Jeremy and others are working on through industry working groups to get even more data out there to help increase adoption of some of these alternative modalities. To stay up to date on the latest news, innovations, and trends in healthcare, please don't forget to check out Pack Talk, a blog written by experts for experts with all sorts of other resources on industry trends and happenings that might be of interest to you. So thank you again and have a great day.
Thank you. Bye.
Thank you all.